Lecture 3, the periodic trends of the representative elements. Representative elements are in groups 1 and 2 and 13 through 18. However, on occasion, the periodic trends we will discuss will not include the noble gases because they just don't fit in the trend. In this first section, we will look at the modern periodic table. The modern periodic table in these slides will present the structure of the periodic table as it relates to our current studies. Just as I indicated at the beginning, groups 1 and 2 over here, and 13 through 18 we call the representative elements, and group 18 the noble gases, because sometimes we do not include the noble gases in the periodic trends that we will be studying. In the middle here, excluding zinc, cadmium, and mercury, are the transition metals. There is some debate as to whether lanthanum and actinium or luteum and lawrencium belong to the transition metals. However, we won't make a distinction between those. We will use lanthanum and actinium on our current periodic table as it is posted in the classroom. And then zinc, cadmium, and mercury are unique in their electron configurations, having their d subshells full, giving them the characteristic of primarily forming +2 cations. As a result, they tend to be grouped together because their chemistry is all fairly similar. At the bottom, as I indicated, are the lanthanides and the actinides. For this lecture series here, we will not be looking at what happens amongst the transition metals or amongst the intertransition metals, but primarily focusing on the representative elements. Well, let's go back to the fun of electron configurations. Excluding the noble gas core of the electron configuration, elements in group 1 have 1 electron going into their subshell. Group 2 have 2 electrons going into their S subshell. Coming over here to group 13, boron and aluminum put their first electron in the P subshell. If we looked at gallium down through nihonium, we would expect those to put their first electron also in the P subshell, but we would also see a full D subshell as indicated next to zinc, cadmium, and mercury. In group 14, we put a second electron in the P subshell. Group 15, we put a third, and I'd like to remind you that in the P subshell, once we get 3, it is half full, which is going to create a breaking point in some of the periodic trends that we will be looking at. In group 16, P4, group 15, P5, and then finally at the noble gases, with the exception of helium, the outer or valence shell is full with 2 electrons in the S and 6 electrons in the P subshell. The interesting characteristic of this is the so-called octet rule basically comes from the fact that the outer electrons involved in bonding are the 2 electrons from the S orbital and the 6 electrons from the P subshell, or the possibility that there are that many electrons involved in the formation of bonds. In the transition metals, the first electron goes in to the d subshell here, for scandium and yttrium, interestingly enough, we would expect to find an electron going in the F subshell when we get to lanthanum and actinium. However, lanthanum and actinium are also D1, as well as luteum and lawrencium at the other end of the intertransition metals. When we get halfway across, we get a half-filled subshell. We will note that this will provide some additional stability in the electron configuration. And then finally, when we get to the end of the transition metals, the D subshell is full. And that provides a lot of stability. Here we can see those valence electrons in their orbital configuration. Just remember, as you're looking at these, the noble gas electron configuration core have been left out. Only the outer electrons are on this table. In group 1, as you can see, 1s1, lithium 2s1, sodium 3s1, and so forth. In group 2, beryllium is 2s2, magnesium 3s2, calcium 4s2, and so forth. Jumping over to group 13, as you can see, now the first electron in the p subshell is added. In group 14, the second electron in the p subshell. In group 15, the third. In group 16, the fourth. And in group 17, the fifth. And then finally, when we get out to the noble gases, helium is 1s2. It has a completely filled s orbital, and then the remainder have 2 in their s orbitals and 6 in their p subshells, giving them a full set of valence electrons. This slide is showing the general electron configuration of the transition metals, again, not including those core electrons from the noble gas electron configuration. And if you look at this, they tend to follow the pattern that we would expect to see, with the exception of these that are in yellow. I think I've talked to you about these before, but here in group 6, chromium and molybdenum have an electron removed from the s orbital and put into the d subshell, so the d subshell is half full. Copper, silver, and gold over here do the same thing. The electron in the s orbital is moved to the d subshell to completely fill the d subshell. These other 4 are just rather odd. There's no good explanation that I can give to you for their orbital construction. However, just note that there are some exceptions. Our first trend is the effective nuclear charge. Basically, we will define the effective nuclear charge as the positive charge felt by an electron where it is in its orbital. Especially, we're going to look at the effective nuclear charge of the valence electrons. A simplistic look at the effective nuclear charge is to subtract out a shielding constant here, which we're going to consider the number of inner or core electrons. For example, the elements in the third period have as their core electrons those 10 electrons that are a part of the neon electron configuration. If we subtract those out from the number of protons, we find that the effective nuclear charge, or we call it Z effective, or ZF, is simply the number of protons, Z, minus 10, to get our number, which is 1, 2, 3, 4, and so forth as we go across the table. Along with the trend, we're going to look at the radius. Note that the radius continually goes down as we go across the periodic table. So these two go together with the Z effective going up, the radius going down. Some smarter people got together and decided, well, maybe there's a better way of establishing this effective nuclear charge by doing some calculations. And what they basically did was calculated some functions and found an effective nuclear charge that did continue to go up as you went across the periodic table, but it matched the radius going down in such a way that if we plot this data, that is the Z effective on one axis and the radius on the other axis, you pretty much get a line with a negative slope. So, in addition to seeing an increasing effective nuclear charge as you go across the periodic table, you will also see that the effective nuclear charge increases as you go up the periodic table. So we are going to basically establish our trends as what happens from the lower left corner as you go up to the upper right hand corner, and the Z effective increases along that diagonal. And we will find that most of our trends will follow this diagonal and will give us either an increasing trend or a decreasing trend. Well, let's take a look at some of the other periodic trends in the elements. Back to atomic radii. Atomic radii are measured as the distance between the two nuclei divided by 2, which will give a radius. In covalent radii, we go from nucleus to nucleus in a covalent bond. Ionic radii work a little differently, where we measure the distance that we would expect from the individual ion. And we will not look at those at this time. But notice, even though there aren't any numbers on here, from lithium going over to neon, they get smaller. So as we go from left to right, the trend is to get smaller. The radius goes down. As we go from the bottom to the top, also look that the radius goes down, giving the net trend as we go from the lower left-hand corner to the upper right-hand corner is a decreasing radius. There are some bumps if you start looking at the transition metals and the intertransition metals, but we're not going to worry about those little bumps and curves. Here is the graph of atomic radii, and again to point out, here is period 2 going down, and here is period 3 going down, and here is period 4 skipping over the transition elements going down, and again period 5 skipping over the transition elements goes down. And we will ignore this little dip thing that occurs in the transition elements. They have their own explanation for how that occurs and why that occurs, and we're not going to worry about it at this time. So again, this establishes in words the trend for the atomic radii, and that is radii decrease as you go up and to the right. The next trend is ionization energy. At the top you can read that the ionization energy is the minimum energy required to move an electron from a gaseous atom in its ground state. In the hydrogen atom, we could actually calculate the ionization energy of the hydrogen electron using the Bohr model. However, this is not possible with the remainder because we have Schrodinger's equation to deal with. Nonetheless, we can set up an experiment to figure these ionization energies out. If an atom has only 2 electrons, like helium, we're only going to talk about the first and the second ionization energies. Lithium will have 3, beryllium will have 4, and so forth. The first ionization energy is always less than the second ionization energy, which is less than the third and the fourth, and so forth. This table shows the ionization energies of some of the elements, that is their first ionization energy. And if you look at it, you will find that ignoring the transition metals, that the ionization energy goes up from group 1 to 2. But then there is a slight decrease over to group 13. See here, beryllium is at 900, boron is at 800. It will then start increasing to nitrogen, and after nitrogen decreases and then finishes increasing across the periodic table. This also occurs in period 3 here, between magnesium and aluminum, and phosphorus and sulfur. Between calcium and gallium, there's only a slight drop. Same for arsenic and selenium. And then the trend down between groups 2 and 13, and then 15 and 16 disappears, and you can think of this leveling out because of the presence of D and F electrons and the D and F subshells. This table shows the first ionization energies of some of the elements. Going across, the first element is potassium. Notice that the first ionization energy to the second ionization energy is a big jump. This occurs with all of the alkali metals. They have 1 electron in the S. The next electron has to come out of the core group. Calcium, the first ionization energy is slightly higher. The second ionization energy goes up, and then there's a jump to the third ionization energy. Again, that jump corresponds basically to the getting into the core electrons. And further looking at that, we can see that here's the core for each of these, and there is a jump corresponding from the valence electrons to the core electrons. Graphically, you can see the bumps in the trend. Here's the beryllium boron decrease from group 12 to 13. Here's the nitrogen oxygen decrease from 15 to 16. The magnesium to aluminum drop, and the phosphorus to sulfur drop there. The overall trend, as you can see, going down the periodic table, is for the ionization energies to go down. The explanation for that is that the electrons are further and further from the nucleus. So here we're again going to look at periods 2 and 3 and the decreases that occur again between groups 2 and 13 and groups 15 and 16. The explanation has to do with the electron configurations. Looking here at group 2, note that the S subshell is filled, stable subshell. Removing an electron is a little bit more difficult. Here in group 13, this electron is at a higher energy level, and removing that electron causes the P subshell to be empty. What we find is that empty subshells, half-filled subshells, and completely filled subshells tend to be more stable. The decrease between groups 15 and 16 are also related to the electron configurations. In group 15, note here that nitrogen and phosphorus have a half-filled P subshell. It is more difficult to take the electron out of there. Over here in group 16, by removing this electron, we create the half-filled subshell, and then we're also removing the electrostatic repulsion between two electrons that are in the same orbital, which makes it also easier to remove. The electron affinity is, by definition, the energy change that occurs when an electron is accepted by an atom in a gaseous state to form an ion. In most cases, the electron affinity is a release of energy when an electron is accepted. There are some cases where it is not. For example, the noble gases do not like to take electrons. The electron affinity is actually the negative of that number on the previous slide. And as you can see, it looks a little bumpy. Here in period 2, going from lithium, there's a bump down. Here there's another bump down. We'll take a look at those shortly. The other is from fluorine to chlorine. It goes up, and then it continues down across the rest of the periodic table. So the general trend on the periodic table is that as you go from left to right, it goes up, and as you go from bottom to top, it also goes up, with the exception of this fluorine-chlorine You would expect fluorine to have a higher electron affinity than chlorine, but we have an actual reason that that does not occur. Here we have the numerical values for the electron affinities, and as we look over here in the noble gases, notice that they are all negative. Here in group 2, these are negative, and then they slowly rise into slightly positive values. Nitrogen is also negative, and then they slowly go up. So as you can see, from 1 to 2, it goes down, goes down, goes down, goes down, goes down. From group 14 to 15, it goes down, goes down, goes down, and then changes once we get the F subshell. Well, why is this occurring between groups 1 and 2 and groups 14 and 15? Well, yep, you guessed it. We're going to talk again. But first, the electron that's added to the fluorine atom goes into the 2p subshell. Although this electron is attracted to the nucleus, the small size of the 2p subshell creates a significant repulsion, and what happens then is that it doesn't release as much energy, and the 2p subshell actually gets a lot bigger than you would expect it to get, compared with that of the chlorine, which goes into the 3p subshell, which is much, much larger. Okay, let's go back and look at these trends again, and the break in the trends that occurs. The first break being between groups 1 and 2, and then the second break we'll look at shortly. Back to those orbital diagrams. As you can see here, in group 1, there's simply one electron in the S subshell, and putting one electron next to it completes the subshell. As a result, you have a completely filled orbital, and there's a release of energy. In the case of adding an electron to the p subshell, you're putting it in an empty subshell. It doesn't like that. You're putting it in a higher energy subshell. It doesn't like that. As a result, many of these release energy, especially in periods 2 and 3, where the orbital sizes are much smaller. Now we go to the group 14 to 15 anomaly. Again, it decreases, 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 and decreases from groups 14. Well, let's look at what's happening here. In group 14, the p subshell is not completely half full. There are only 2 electrons in that subshell. Adding an electron makes the subshell half full. We get a lot of energy back, more stable. In group 15, the addition of the electron breaks the symmetry involved with a half-filled subshell, creates additional electrostatic repulsion. As a result, you get less energy back, and in the case of nitrogen, it does not like to do that at all. The final trend we're going to look at is metallic character. But first, let's look at the metals, their characteristics. Metals are shiny, lustrous, malleable. That is, you can bend them, shape them. They're ductile. You can make them into wires. They conduct heat and electricity very well. And they tend to have low ionization energies, meaning that they readily form cations. Non-metals, however, are different. They come in a variety of colors. They're usually not shiny, brittle, generally poor conductors of heat and electricity, and they tend to form anions. That is, they have high electron affinities. The metalloids are kind of intermediate between the metals and nonmetals, and they are also called semiconductors. Metallic character increases from the top to the bottom and decreases from left to right, giving us a trend if we were to again look at the periodic table. The greatest metallic character is here in the lower left. Going to the upper right, it's the least. So metallic character goes down as you go up and across the periodic table. Electronegativity is a trend that we generally look at in bonding. I introduce it here because it's also one of the additional trends, and I like to show them all. Electronegativity is an artificial number. Basically, we're saying it's the ability of an atom to attract electrons towards itself in a chemical bond. It is a relative scale. It is a created number. We find that fluorine in the upper right-hand corner of the periodic table has the highest electronegativity, and francium, which is in the lower left-hand corner, is the lowest. And here's the table. Again, francium down here, lowest. Fluorine up here, highest. Note here, krypton and xenon do have electronegativities. They do participate in bonding. But I want to lay on top of this periodic table here the trends. Because we've looked at several trends, and we can match them all up on one table. If we look at an arrow going from the lower left to the upper right and talk about the trends. The first one was the effective nuclear charge. The effective nuclear charge, as we went across the periodic table, went up. Effective nuclear charge went up. The radius was the next trend, and the radius goes in the opposite direction of the effective nuclear charge, and the radius goes down. We next looked at ionization energy. Ionization energy generally goes up as you go from the lower left to the upper right, but it had two anomalies. The first anomaly was between groups 12 and between groups 2 and 13, and then the next one was between groups 15 and 16. Following electron affinity, ionization energy, we had electron affinity. It goes up as you go up the table and across, but it also showed anomalies. The anomalies were between groups 1 and 2, and then 14 and 15. Note that the anomalies for ionization energy and electron affinity only differ by one group, with electron affinity coming first between groups 1 and 2, 14 and 15, and ionization energy between groups 2 and 13, and then 15 and 16. That's 4 of the trends. Next one that we put on there was metallic character. Metallic character was greatest over here with francium, and least in the upper right hand corner. So metallic character goes down as you go up and across the periodic table. And then the last one was not effective nuclear charge, pardon me. The last one was electron affinity. Well, I'm really messing this one up. Electronegativity. Electronegativity, as you go up the periodic table and across, it goes up. Nicely, you can group these all together. The effective nuclear charge, Z effective, ionization energy, electron affinity, and electronegativity all go up as you go from the lower left to the upper right hand corners, whereas radius and metallic character go down as you go up and across the periodic table. And then remember that ionization energy and electron affinity had anomalies. The electron affinity anomaly comes first, groups 1 and 2, and then 14 and 15, and the groups 2 to 13 and 15 to 16 were the anomalies for the ionization energy. This here's your trend summary. Puts it all together so that you have a table to work with. Again, let me note here. Atomic radius, metallic character, decrease, decrease. The others increase. The anomalies first occur in electron affinity, and a group later occur in ionization energy.